We are now going to talk about two more rules that we can use to help us as we try and find derivatives. The first rule we will discuss is called the product rule, and the second rule is called the quotient rule. And these are probably words you've dealt with before in math. And product normally implies multiplication, quotient rule implies division, and that's sort of what's going on here. And we've already learned how to take derivatives of expressions using the power rule, two different terms. What we're going to learn now, instead of two terms, what if we multiply them? And in the world of math, when you multiply things together, you call them factors. So you can think of this first parenthesis as a first factor and the second factor. Sometimes you'll hear me even call these functions. This is sort of like a little function or expression. But anyways, here we're multiplying them. Now let me first highlight something that I hope will not confuse all of you, because one of the things you learn if you've been in math for very long, there are almost always multiple ways to solve a problem. Or sometimes I like to say, many ways to skin a cat. Actually, I don't know why people skin cats. It doesn't sound very nice, but it's a pretty famous phrase. So let me go ahead and let me explain the product rule, and we'll apply the product rule to this problem. But then I'm also going to show you a second way to solve this problem, and the problem is obviously to find the derivative. The product rule is used when you're multiplying two factors together. Now let me simply state in words what the product rule is. If you look in your book, they probably have a nice formal math definition, but sometimes trying to read math definitions and all the math lingo and formulas and stuff can be a bit confusing. So here's what you'll hear me say over and over again of how to implement the product rule. So when you take the derivative of a product rule, maybe I'll do it in steps. I'm just going to say copy the first. By that I mean the first factor, the first function. So in our case, I'm thinking of this as like the first function, the first factor, the second. So you simply copy down the first one. Then you multiply by the derivative of the second. So you take your second factor. Now I can, in my head, take this derivative. It's pretty easy, right? Derivative of 2x squared is just 4x. So I multiply by the derivative of the second factor. So it's almost like the first times derivative of the second. And then you do addition plus, then copy the second factor. Second factor is 2x squared. And then you multiply by the derivative of the first factor. So here's the second one. Derivative of 10x to the sixth is 60 x to the fifth. So if I try and simplify this, 40 x to the seventh plus 120 x to the seventh, and actually these are like terms. So the derivative is, hopefully if I didn't make a mistake, 160 x to the seventh. So here's the product rule. Once again, just to say it again, you got these two factors. I always write down the first. By write it down, I mean copy it. Write down the first times the derivative of the second plus the second times the derivative of the first. So you end up adding these together and you just flip them. On one of them, you write down, you copy down one of them, you multiply by the derivative of the other, and you take the other one and multiply by the derivative. And I always, you'll hear me say when I do examples, I always say write down the first, derivative the second. Theoretically, you could start with the second times the derivative of the first. Since you're adding these together, doesn't matter which one of these you do first, but that's just the way I always do it. Let's do another one. We'll make it even simpler. No coefficients. Here's my original function. Maybe I'll put them in parentheses. X squared times x to the fifth. Now some of you are probably be thinking something, but hold on, I'm gonna talk about that in a minute. I want to go ahead and apply the product rule to find this derivative. So the first times the derivative of the second plus the second times the derivative of the first. So this becomes 5x to the sixth plus 2x to the sixth equals 7x to the sixth. So that's two applications of the product rule. Now here's where I'm going to show you an alternate way to find the derivatives of these two. And maybe you've already thought about this. And actually this second way is probably easier. It's probably less work. Although we're going to do some problems in a minute where you don't really have a choice. There's only really one reasonable way. And that is the first problem I gave you was 10x to the sixth times 2x squared. And we applied the product rule and thought of these two as sort of separate factors or functions. But you could have actually, from the start, just multiplied x to the sixth times x squared is x to the eighth. You could have, from the start, sort of simplified, and then you could take the derivative and apply your power rule. And you notice you get the same answer. And this way is probably simpler. However, I want to do it this way just to show you that this thing called the power rule works. So no matter if you use the power rule or just simplify, use the power rule, you get the same answer. So it sort of confirms the power rule worked. And in the same way, in that second one, which is even simpler, if I want to find the derivative of this, earlier I applied the power rule, which to be honest is probably some extra work, right? That's what I did here. we could have from the start just said, well, this is x to the 7th. What's the derivative of x to the 7th? It's just 7x to the 6th, which is what we got here. So yes, some of you, when I was up here using the power rule, you may have thought to yourself, well, that seems like a lot of extra work when you can just do this, and you're correct. But I did this just to show you that the power rule works. You get the same answer as if you do it the easier, more clever way. But now let's look at some problems where the power rule, I wouldn't say is your only option, but it's the least painful option. So we'll start with one that we'll maybe say y equals x squared minus x plus 1 times, in parentheses, x squared minus 3. And we want to take the derivative of this. So you look at this and you say, okay, we could use the power rule, which actually I'm going to do in a minute. So this first parentheses, like your first factor, here's your second factor, you use the power rule. Someone could, if they wanted to, they could go ahead and multiply out these parentheses, and you get a bunch of terms, and then you could take the power rule, or take the derivative using the power rule. For me, it's like, I don't really have a desire to do massive algebra multiplying x squared times x squared times minus 3, minus x times x squared. I mean, sure, I could do it, but it seems like a lot of work. So this is a case where, to me, unlike the first couple problems we did, I think the power rule might be easier. Let's see. So I'm going to write down the first times the derivative of the second. So now I take the derivative of what's inside the parenthesis. I've got two terms here. So if I'm going to take the derivative, I do them one at a time. What's the derivative of x squared? Well, it's 2x. What's the derivative of minus 3? Well, minus 3 is a constant. Derivative of a constant is just 0. So actually, the derivative of this parenthesis is just 2x. So the first times derivative of the second plus the second. So I copy down my second parenthesis times the derivative of the first. This first parenthesis, I have 3 terms. I take the derivative one at a time. So it's 2x minus 1. So now, in the world of math, normally they like to simplify, and simplifying would mean multiply out these parentheses, maybe combine like terms. So if I distribute the 2x in this first parenthesis, 2x cubed minus 2x squared plus 2x. If I FOIL this, it'd be 2x cubed minus x squared minus 6x plus 3. All right, still some algebra involved. Now if I combine like terms, 2x cubed plus 2x cubed, I'm going to mark these off to keep track of them. Negative 2x squared minus x squared minus 3x squared. 2x minus 6x. And then plus 3. All right, hope I didn't make any mistakes, but that's the derivative. Let's do a few more. How about x squared times 3 square root of x plus 2. So square root of x makes this sort of ugly. Matter of fact, in this class, almost always, whenever you see a radical, first thing we do is convert it to a rational exponent. Now, I guess you could multiply out the parentheses, but you're dealing with sort of messy exponents. Let's just go ahead and use the product rule to take the derivative. So like this is my sort of my first factor or first function and the second one. So you write down the first times the derivative of the second one. Well, this is a constant, so that's just 0. So I've got 3, 1/2 comes down front. When you subtract 1 from the exponent. So that's the first half of the product rule. The first times derivative of the second plus the second times derivative of the first, which is just 2x. Now you're going to learn in this class, oftentimes when you start taking derivatives, things can get very messy. You can do what you can to try and simplify and combine. Maybe once in a while things cancel out. But a lot of times you just end up with some messy, ugly sort of algebra expressions. So for instance, this one, 3 times 1/2 is 3/2. X squared times x to the negative 1/2 is really going to be x to the 3/2. So this is 3/2 x to the 3/2. And if I distribute this 2x, I would have 6x to the 3/2 plus 4x. Now these two are actually like terms, so I can combine those. So 3/2 plus 6, 6 is 12, that's like 15/2. X to the 3/2 plus 4x. Not real pretty, you got this rational exponent, but, and actually you can check, because this came out of a book I'm using. I'm going to see if I did it correct, hoping to make any mistakes. And yes, that is the correct answer. So product rule, let me do one more. How about, so this one, it's good practice sometimes. We almost always use f of x and y and stuff, but functions don't always have to be f of x. This one is g of t. So in a sense, t is sort of like your x and g is like your f. But anyways, so now the variable I'm working with is t plus 2/t times t squared minus 3. I mean, theoretically, you could try and FOIL these parentheses, take derivative, but that looks sort of messy. Let's just try and see what happens if we use the product rule. So the first times derivative of the second, which is just going to be 2t, plus the second times derivative of the first. Now I should have maybe done this, but I should have rewritten this. 2/t. I'm going to need to rewrite it as 2 times t to the minus first, because when I take the derivative of this, I want to use the power rule. So this is just going to be 1. And this is going to be, I'm going to try and do this in my head, maybe skip some steps. So the minus 1 comes down front. So 2 times minus 1 is minus 2. And you subtract 1. So I think it's going to be, whoops, I think it's a minus 2t to the minus 2. Let's check on that. Derivative of this is going to be minus 2t to the minus 2. You can see this is already getting messy, but in order to simplify it, let's try and multiply out. So 2t times t is 2t squared. 2t times 2 over t is 4, and the t's cancel. Now this I have to FOIL. I've got two terms in each. T squared times 1 is just t squared. T squared times minus 2t to the negative 2. The t's actually cancel out. Just left with minus 2. Minus 3 times 1 is minus 3. And minus 3 times minus 2t to the minus 2 is minus 6t to the minus 2. Like I said, messy algebra. Combine like terms, 2t squared plus t squared, 3t squared. I've got some numbers here. 4 minus 2 plus 3, I think it's minus 1. Now this one, I'll go ahead and get rid of the negative exponents. And once again, I have the answer for this. Let's see, hopefully I didn't mess up. And I see a different answer. Make sure I copy the problem down correctly. So here's a case where my answer, oh, I looked at the wrong problem. Sorry. Wow, I had me nervous for a second. So this is number, in my book, number 35. 3t squared minus 1 minus, oh, wrong sign here. Where did it, oh yeah. Minus 3 times minus 2t squared. Some of you probably noticed that. It's a good thing I checked the answer. And this is correct. So that's the product rule, all right? You're going to use the product rule a lot when we take derivatives. Now let's look at the other rule we're going to talk about called the quotient rule. So product rule, you notice, like we ended up multiplying two factors. Quotient rule, as you can imagine, is where we're doing some dividing. So for instance, once again, to take a very basic example, where to be honest, you probably want to not even use a quotient rule, but I want to just show you what it is. So this one, if you were actually doing this problem and you were asked to find the derivative, you would honestly be sort of crazy to use the quotient rule. Because what you really should do here is realize that these cancel out and simplifies to x squared. And then the derivative is 2x. But just for fun, let me do what I did with the product rule. Let me give you explain the quotient rule, and then apply it here, even though it's crazy to do it, but just to prove that you get the same answer. So the quotient rule, most of the time, and what I teach is a little phrase that you say in your head. And here's the phrase. So I'm not going to give steps. It's a little phrase. And if you follow the phrase, then you'll have applied the quotient rule. And you say low D high. And I'll explain what this means in a minute. Minus high V low over low squared. So the high and the low is talking about sort of the top and the bottom. High meaning it's high and low meaning it's low. And every time you have this d here, the d means to take the derivative. So what this is really saying is you take the low term, the term in the bottom, you multiply it by the derivative of the high term. Then you subtract the high term times the derivative of the low term, and you take all of that and you divide it by the low term squared. Now you probably have a little bit of a hunch that when you start applying the quotient rule, things can get very messy. You have a fraction, you have all kinds of stuff going on. But the key is, the little phrase is low d high minus high d low over low squared. I guess the key is you got to remember, for me, it starts out with low. Low d high minus high. Some people might say high d low minus, you can't do it. The order here has to be low d high. Because we're subtracting, you can't switch these. If you switch these, it's going to be wrong. It's always low d high minus high d low over low squared. So just for fun, even though it's sort of crazy, let's apply the quotient rule to this situation. I mean, it won't be that hard, but there'd be no reason to do it, but just to sort of prove you get the same answer. So if I apply the quotient rule, so this is my high, this is my low. So low d high. Low d high means low times the derivative of what's in the top, 6x to the 5th, minus high d low, derivative of what's in the bottom, 4x cubed, over the low squared, x to the 4th squared is x to the 8th. So you can see this is a lot more work than this. But let's simplify this and just see if we can get the same answer. So this is going to be 6x to the 9th minus 4x to the 9th over x to the 8th. We can combine these. 6x minus my 4x to the 9th, that's 2x to the 9th over x to the 8th, and by the time we cancel, 2x. So yes, you in fact get the same answer. But of course, you would never do this because this is so much simpler. However, what if you were given this function and they want to know the derivative? I can't simplify this. I can't cancel things out. I have no choice but to apply, excuse me, the product rule if I want to get this answer. So let's do it. Let's apply the product rule. The quotient rule. Low d high. Low d high. Derivative of t is just 1 minus high d low. What's the derivative of t squared minus 1? 2t over the low squared. And oftentimes when you square this, low is what makes it sort of messy. Because I can probably simplify the numerator. It's just t squared minus 1. Hopefully see t squared minus 1 minus 2t squared. So you end up with really negative t squared minus 1 over t squared minus 1 squared. Now, I don't think this, if possible, you would always try and simplify and cancel. I don't think And just to prove it, I could sort of factor out the minus to make it look a little better. But nothing cancels out. This is sort of a messy answer, but it is what it is. Let me do one or two more. How about this one? Let's write it as y. Y equals 8x cubed minus 1 over 2x minus 1. And we want to determine the derivative. Quotient rule is the only option here. Doesn't simplify, nothing you can do. It's got to be quotient rule. Low, D high. What's the derivative of what's in the top here? Well, the first part's 24 x squared. Derivative of negative 1 is just 0. So the derivative of the high is just 24x squared minus high D low. What's derivative of 2x minus 1? It's just 2. All divided by the low squared. So now, do what you can to simplify. May not be a whole lot I can do. And we're going to multiply out the parentheses and the top. So this would be 48x cubed minus 24x squared. And this would be negative 16x cubed. Got the minus here and a minus here, so I think it's going to be plus 2 all over 2x minus 1 squared. So I can combine some like terms. And I can squeeze it in over here. So it looks like 48x cubed minus 16x cubed, which is 32x cubed minus 24x squared plus 2 all over this 2x minus 1 squared. And that's pretty much it. I mean, I could factor a 2 out of the top, but pretty messy. But in this one, actually, I can check my answer and make sure I didn't make any mistakes, because that does happen. Yeah, I think that's correct. All right, let me do one more and then we're done. So product rule and quotient rule, not the concept, I don't think is that hard. Sometimes the algebra gets messy. What if we have this x over 3 minus x? Now this one's interesting because we have two terms here. Of course, the first term is this sort of fraction. And then you got this. We learn when you take the derivative, you just take derivative one term at a time. The second term is pretty straightforward, right? However, I take the derivative of the first term. Since it's a fraction here, what I have to do is to take the derivative of the first term, I have to apply the quotient rule to this first term. So it's almost like a problem within a problem. So to take the derivative, I'm going to take derivative of these one at a time, and I'm going to do this fraction first, but to take the derivative of this fraction, I have to apply the quotient rule. All right, let's do that. So low d high, derivative of x is just 1, minus high, d low, derivative of 3 minus x is just minus 1, all over the low squared. So that right there is the derivative of the first term. Then I add to it the derivative of the second term, which is pretty straightforward using the power rule, plus 15x squared. Now what I should probably do is try and simplify this numerator, but then after that, there may not be a whole lot to do. So this is actually 3 minus x plus x. So 3 minus x plus x, the x's actually cancel. I'm left with 3 over 3 minus x squared plus 15x squared. That is correct. All right, so product rule and quotient rule. You're going to have to use them. They're not that hard. The quotient rule especially can make derivative very messy, but it is what it is. All right.